All right, let's talk about one of the most classic and, let's be honest, kind of scary coding interview questions. But today, we're not just going to dryly list facts. Nope. We're going to tell a story. A story about how you can absolutely ace this interview, not by memorizing, but by really getting it. So let's dive in.
Okay, so picture this. Your name is Arjun, you're in the final round. The whiteboard is staring back at you totally blank. You've got the marker in your hand, and then the interviewer drops this bomb. The clock starts ticking in your head. You can feel the pressure building, right?
And then it happens. Total brain freeze. Come on, we've all been there, right? That horrible moment of panic when a concept you know you studied just, poof, vanishes. But hey, don't worry. Arjun and you are about to get a little help from a friend.
And this is where our mentor for today, Neha, steps into the picture. She's going to walk us through this whole thing. But here's the key. We're not just looking for the answer. We're hunting for the understanding behind it. First things first, let's really get what the problem is all about.
So, let me introduce you to someone. This is Mr. Cache. Yeah, he's a little dramatic, but honestly, he nails the core problem. A cache is just a small, wicked fast chunk of memory, but it's got a fixed size. Think about your web browser's cache, right? It saves images so websites load faster next time. But the second you try to stuff one more thing in there when it's full, well, something's got to go. The real question is, what gets the boot? For an LRU cache, the rule is super simple. Out with the old. Whichever item has just been sitting there, collecting dust, untouched for the longest, that's the one that gets kicked out. So the big puzzle is, how do we build a system that can keep track of this efficiently?
Okay, piece number one of our puzzle is the hash map. You got to think of this thing's superpower as pure speed. We need to be able to find any item in our cache like instantly, without digging through everything. The hash map gives us that beautiful O of 1, or constant time access. And what that really means is it takes the exact same amount of time to find an item, whether your cache has 10 things in it or 10 million. Crazy fast.
But here's the catch. A hash map is great for speed, but it has no idea about the order of things. It doesn't know what you used last. And for that, we need our second component, the doubly linked list. Now, the magic here is that every single node knows its neighbors, the one before it and the one after it. And because of that, we can snatch a node and move it around, especially to the front or the back, super fast. And this is where the magic happens. When these two team up, it's like a power combo. The hash map stores the key and a pointer straight to the node in our doubly linked list. So what do we get? The best of both worlds. We get the instant lookup from the map, and we get this perfectly ordered list that tracks usage. The very front of the list, that's our most recently used VIP section. And the very back? Yeah, that's the danger zone, where items are about to get evicted.
Okay, so let's walk through it. Say we want to get an item. Step 1. We use our super fast hash map to find its node in the list. O of 1. Bam. Done. Easy peasy.
But we're not done. Because we just used that item, we have to update its status. We basically just pluck that node from wherever it was sitting in the list and zip it right to the front, making it the new most recently used item. And here's the really crucial part. That move is also a constant time operation. That's the secret sauce to the whole thing's efficiency. And look at that. Here's the beautiful result. Getting an item? O of 1. Putting a new item in, which means adding to the front and maybe kicking one out from the back, also O of 1. That is the gold standard for efficiency, people. We've just built a perfectly optimal LOU cache. Arjun's feeling pretty good right now. He's thinking he nailed it.
But just as he's about to relax, the interviewer leans forward with this little smile. You know that smile. The challenge is not over, not by a long shot.
And then she drops the follow-up question. This isn't about when you use something anymore. Oh no, now it's about how often.
And you can just see the thought bubble over Arjun's head, right? It's exactly what we'd all be thinking. This isn't just a single question. It's got levels. It's a challenge designed to see how deep your understanding really goes. So, what in the world is an LFU cache?
All right, time to level up. This next part, it requires a totally different way of thinking. But don't worry, we're going to break it down with the same clear step-by-step approach.
So the whole game changes here. LFU, least frequently used, could not care less about when you last touched an item. All it cares about is how many times you've touched it. So when the cache gets full, the item with the absolute lowest access count, that's the one that's out.
Oh look, Mr. Kashish is back, and he's more dramatic than ever. See, in his world, it's a popularity contest.
Pure and simple. If an item isn't getting a lot of attention, if it's not being accessed frequently, it's on the chopping block. Doesn't matter if you just put it in there 5 seconds ago.
Okay, to solve this one, our data structure has to get a little bit fancier. We're going to need 2 hash maps this time. The first one is pretty familiar. Maps are key to its value and, importantly, its current frequency count. But the real genius is the second hash map. Here, the keys are the frequencies themselves. You know, a frequency of 1, 2, 5, whatever. And the values? They're separate doubly linked lists containing all the items that share that exact frequency. So now when we need to evict someone, we just find the list for the lowest frequency and pop an item off. And to make that part instant, we'll keep a simple little variable, minfreg, that always points us to the right list to evict from.
I know. It's definitely more complex under the hood. There are more moving parts. But the result? It's seriously impressive. Because with this clever 2-map structure, we still achieve O of 1 time complexity for both getting and putting. We're still hitting that gold standard of performance. Pretty cool, right?
Okay, so at this point, Arjun gets both systems. He's feeling way better. But just understanding them isn't enough to ace the interview. You got to be able to compare them, contrast them, and you definitely need to know the common traps people fall into.
So let's do a quick face-off. LRU versus LFU. The eviction policy for LRU is all about recency, the when. For LFU, it's all about frequency, the how often. This fundamental difference makes the LRU implementation quite a bit simpler, which is exactly why it's such a common starting point in interviews. LFU, that's the advanced follow-up, the curveball they throw to see if you can handle something more complex.
And you better believe Mr. Cache is going to be watching your code like a hawk. The number one, absolute biggest mistake you can make is building a solution that isn't efficient. If your code has to search or loop through the cache to do anything, that's a huge red flag. It's got to be O of 1.
So let's list out these common traps so you can avoid them. First, for LRU, don't just use a simple queue or array. Why? Because you'll have to search for an item to move it, and that's a slow O of n operation. Dead end. Second, don't forget to make your linked list doubly linked. Without that previous pointer, you can't remove a node from the middle efficiently. And for LFU, if you don't correctly track that minfreq variable, eviction turns from an instant operation into a painful search. Remember, the goal is always, always, always O of 1.
And that brings us to Neha's final, most important piece of advice. This is the big takeaway from our whole story today. Please, don't just memorize the code. You have to understand the story. Ask yourself, why? Why a hash map? Because we need speed. Why a doubly linked list? Because we need to maintain order. Why does LFU need 2 maps? So we can track frequency in constant time. Once you truly understand the why, the story behind the data structures, the code just becomes the language you use to tell that story. And that, my friends, is how you walk in and absolutely ace the cache interview.